Welcome to GKE Shared VPC. Welcome to the channel. Please consider subscribing. I produce videos covering AWS, Azure, and GCP on a daily basis. Please also hit the bell button to get notified. I appreciate your subscription in advance. Welcome to our comprehensive guide on setting up GKE clusters with Shared VPC. This presentation will take you through everything you need to know to implement enterprise-grade Kubernetes infrastructure in Google Cloud. We will start by understanding what Shared VPC is and why it is crucial for enterprise environments. Think of Shared VPC as the networking foundation that allows multiple teams to work independently while sharing common infrastructure resources. Throughout this presentation, you will learn practical implementation steps, see detailed network architecture diagrams, and understand every G-Cloud command parameter. By the end, you will be able to set up production-ready GKE clusters that follow Google Cloud best practices. Understanding Shared VPC architecture. Let me explain the fundamental architecture of Shared VPC. Imagine you're managing a large organization with multiple development teams. Each team needs their own project for billing and access control, but they all need to communicate securely. Traditional VPC peering becomes complex and expensive when you have many projects. Shared VPC solves this by creating a hub-and-spoke model where one host project owns the network infrastructure, and multiple service projects attached to it. This diagram shows how the host project contains all networking resources, the VPC, subnets, firewall rules, NAT gateways, and VPN connections. Service projects then attach to specific subnets based on their environment needs. Notice how each environment, production, staging, development, gets its own subnet with dedicated IP ranges, but they all share the same underlying network infrastructure. This provides isolation while enabling resource sharing. Project roles and responsibilities. Understanding the different project types and their roles is crucial for successful Shared VPC implementation. Let me walk you through each component and who typically manages what. The host project is managed by your platform or network team. They are responsible for the core networking infrastructure, creating subnets, managing firewall rules, setting up VPN connections, and ensuring overall network security. Think of them as the network landlords. Service projects are managed by individual application teams. They can deploy their applications, create GKE clusters, and manage their own resources, but they use the network infrastructure provided by the host project. They are like tenants in the shared network. The IAM roles shown here implement the principle of least privilege. Each person only gets the permissions they need for their specific responsibilities. This separation ensures security while enabling team autonomy. Benefits of Shared VPC for GKE. Now let's discuss why Shared VPC is particularly valuable for GKE deployments. In traditional setups, each team might create their own VPC, leading to network fragmentation and increased costs. With Shared VPC, you can implement enterprise-grade network architecture patterns. For example, you can have dedicated subnets for different environments. Production workloads get high-performance subnets with strict security, while development environments get cost-optimized configurations. The cost benefits are significant. Instead of each project paying for its own NAT gateway, which costs about $45 each, all projects share a single NAT gateway. Similarly, VPN connections, load balancers, and other network infrastructure are shared. Security is enhanced because network policies are centrally managed. Your security team can enforce organization-wide rules without needing access to individual application projects. This is crucial for compliance in regulated industries. Critical IP address planning. Let me walk you through one of the most critical aspects of Shared VPC setup, IP address planning. This is where many implementations fail, because overlapping IP ranges cause connectivity issues that are difficult to troubleshoot later. For GKE clusters, you need three types of IP ranges. Primary ranges for the nodes themselves, secondary ranges for pod IPs, and secondary ranges for service IPs. Each cluster needs its own non-overlapping ranges. I recommend using this systematic approach. Production gets the ranges starting with 10.0.1.x and 10.10 to 20.x. Staging gets the ranges starting with 10.0.2.x and 10.30 to 40.x. And development gets the ranges starting with 10.0.3.x and 10.50 to 60.x. This provides clear separation and room for growth. The pod ranges are large, /14 networks, because Kubernetes clusters can scale to thousands of pods. The service ranges are smaller, /16 networks, since you typically have fewer services than pods. Always consider your on-premises network ranges and any existing cloud infrastructure when planning. Document these ranges and get them approved by your network team before implementation. Understanding traffic flow. Now let's examine how traffic flows through a shared VPC architecture. This sequence diagram shows a complete request lifecycle from an external user to your applications and back. Notice how the global load balancer in the host project receives the initial request and routes it to the appropriate service project. This is powerful because you can have multiple applications across different projects all accessible through the same load balancer with consistent SSL certificates and routing rules. Internal communication between service projects is one of the biggest benefits. When the production cluster needs to call the staging cluster for validation, that traffic stays entirely within the shared VPC. There are no egress charges for this internal communication, which can save significant money in microservices architectures. External API calls go through the shared Cloud NAT gateway, which means all your projects present the same external IP addresses. This simplifies firewall rules with external systems and provides consistent outbound connectivity. The key insight here is that while projects remain separate for billing and access control, network traffic flows efficiently through shared infrastructure. Prerequisites and setup overview. Before we dive into the actual implementation, let's review what you need to have in place. This preparation phase is crucial. Skipping these steps will cause problems later. First, you need the appropriate IAM permissions. The setup process requires organization-level permissions to enable shared VPC and project-level permissions to configure networking. Make sure you have these permissions or work with someone who does. You'll need at least 2 projects. One host project for networking and at least one service project for your applications. I recommend creating separate projects for different environments, prod, staging, and dev, from the beginning. The G-Cloud CLI should be installed and configured with your credentials. We'll be using many G-Cloud commands with specific parameters, and I'll explain each one in detail. Finally, think about your organization's network architecture. Do you have on-premises networks? What IP ranges are already in use? These considerations will affect your IP planning decisions. Host project initialization. Now we will start the actual implementation by setting up the host project. This is where all the network infrastructure will live. The first step is enabling the necessary APIs. The Compute API provides VPC and networking capabilities. The Container API is needed for GKE integration. The Service Networking API enables private services like Cloud SQL with private IPs. The Resource Manager API allows project-level operations. The G-Cloud Compute Shared VPC Enable command is the key step that converts a regular project into a shared VPC host project. Once you run this command, the project can share its network resources with other projects. Notice how we set the project context first using the G-Cloud config set project command. This ensures all subsequent commands operate on the correct project. I always recommend setting environment variables for project IDs to avoid mistakes. These API enablement commands may take a few minutes to complete. Each API activation sets up the necessary backend services for that functionality, creating the VPC network infrastructure. Now we will create the actual network infrastructure. We start with the VPC network itself, then create the subnets that will host our GKE clusters. The VPC network is created with custom subnet mode, which means we manually define all subnets. This gives us complete control over IP address allocation. The global BGP routing mode enables dynamic routing across regions. For each subnet, we define both primary and secondary IP ranges. The primary range is for the GKE nodes. These are the actual virtual machines running Kubernetes. The secondary ranges are for pods and services within the Kubernetes clusters. Notice the Enable Private IP Google Access flag. This is crucial for clusters without external IPs. It allows nodes to reach Google APIs and services using private IP addresses. Without this, your pods will not be able to pull container images or access Google Cloud services. Each environment gets its own subnet with dedicated IP ranges. This provides network-level isolation between environments while keeping them in the same VPC for efficient communication. Network security with firewall rules. Network security is implemented through centralized firewall rules in the host project. These rules apply to all service projects using the shared VPC, giving you consistent security policies across your entire infrastructure. The first rule allows internal communication within the VPC. This is essential for Kubernetes clusters to function. Pods need to communicate with each other, with the control plane, and with Google Cloud services. The health check rule is crucial for load balancers. Google's load balancers perform health checks from specific IP ranges, and without this rule, your services won't be considered healthy and won't receive traffic. The environment isolation rule demonstrates advanced firewall capabilities. By creating a deny rule with higher priority, we prevent production workloads from accessing staging or development environments. This is critical for compliance in many organizations. Notice how we use network tags to target specific instances. Tags provide flexible targeting without needing to specify individual IPs. GKE automatically applies appropriate tags to cluster nodes. The SSH access rule shows how to enable administrative access from your corporate network. Replace the example IP range with your actual corporate CIDR blocks. Infrastructure setup. Now, we'll set up the shared network infrastructure that all service projects will use. This is one of the key benefits of shared VPC. Expensive network resources, like NAT gateways and VPN connections, are shared across all projects. The cloud router is the foundation for dynamic routing in Google Cloud. It manages BGP sessions and enables features like Cloud NAT. Think of it as the brain that handles routing decisions for your VPC. Cloud NAT provides outbound internet connectivity for instances without external IP addresses. In our setup, all GKE clusters will use private nodes, so they need NAT for internet access to pull container images, reach APIs, and download software. The VPN gateway enables secure connectivity to on-premises networks. By placing it in the host project, all service projects can access corporate resources through a single, managed connection. Service project attachment process. Attaching service projects to the shared VPC is a critical step that establishes the trust relationship between projects. This process grants service projects permission to use the host project's network resources. The attachment process is straightforward but has important security implications. Once attached, the service project can create resources that use the shared network, but it still maintains project-level isolation for billing, access control, and resource management. We're setting up 3 service projects representing a typical enterprise scenario: production, staging, and development environments. Each will have different resource requirements and security policies. Always verify the attachment was successful before proceeding. Misconfigurations at this stage will cause problems when creating GKE clusters later. Critical IAM configuration. IAM configuration is where many shared VPCs implementations fail. The permissions must be precisely configured to allow GKE service accounts to operate in the shared network while maintaining security boundaries. The GKE service account needs 2 key roles. Compute Network User allows it to use network resources, and Container Host Service Agent User enables it to manage resources in the host project on behalf of GKE. Subnet level permissions implement the principle of least privilege. Instead of granting access to the entire VPC, we grant access only to the specific subnet each project should use. Notice how we configure permissions for each environment separately. Production clusters can only access production subnets. Staging clusters only access staging subnets, and so on. Production GKE Cluster Design. The production cluster configuration represents enterprise-grade Kubernetes infrastructure. Every parameter here is chosen for security, reliability, and performance in production environments. Private nodes are essential for security. They have no external IP addresses and rely on CloudNet for outbound connectivity. The master IP version 4 CIDR block parameter creates a private control plane that's only accessible through the VPC. Network policies enable microsegmentation within the cluster. This is crucial for multi-tenant environments where different applications need network isolation. Shielded nodes provide additional security through secure boot and virtual TPM. This protects against rootkits and other low-level attacks. Workload ID is the modern way to handle service account authentication without JSON keys. Staging environment configuration. The staging cluster balances production-like features with cost optimization. It is designed to closely mirror production for accurate testing, while using fewer resources. Notice the different machine type. The E2 Standard 2 provides adequate performance for testing while costing significantly less than the N1 Standard 4 instances used in production. The Rapid Release Channel enables testing of new GKE features before they reach production. This allows you to validate new capabilities and identify potential issues early. Smaller autoscaling limits of 1 to 5 nodes reflect the typically lower load in staging environments while still enabling scale testing. All the security features like private nodes and network policies are maintained to ensure staging accurately represents production security posture. Development environment optimization. The development cluster is optimized for cost and flexibility rather than production-grade reliability. Developers need quick iteration cycles and low costs for experimental workloads. The key cost optimization is preemptible nodes, which can be interrupted but cost up to 80% less than regular instances. This is perfect for development workloads that can tolerate interruptions. Min nodes set to 0 means the cluster can scale down completely when not in use, eliminating costs during nights and weekends. This can provide significant savings for development environments. Smaller machine types, E2 medium, and standard persistent disks provide adequate performance for development while minimizing costs. Connectivity verification process. After creating the clusters, verification is crucial to ensure everything is working correctly. These tests validate that the shared VPC configuration is functioning as expected. Getting credentials for all clusters sets up kubectl contexts, allowing you to manage multiple clusters from a single workstation. The context names follow a specific pattern that includes project ID and cluster name. Deploying test workloads provides a simple way to verify that clusters can pull container images, schedule pods, and allocate IP addresses from the shared VPC's ranges. Creating services tests the Kubernetes networking stack and validates that the secondary IP ranges for services are working correctly. Workload identity implementation. Workload identity is the secure, Google-recommended way for applications running on GKE to access Google Cloud services. It eliminates the need for service account JSON keys, which are a security risk. The process involves creating both a Google Cloud Service account and a Kubernetes service account, then binding them together. This allows Kubernetes pods to impersonate the Google Service account. The IAM policy binding is the key step. It grants the Kubernetes Service account permission to impersonate the Google Service account. The annotation on the Kubernetes Service account completes the binding, telling GKE which Google Service account to use when pods use this Kubernetes Service account. Network security policies. Network policies provide microsegmentation within Kubernetes clusters. They are essential for multi-tenant environments and defense in-depth security strategies. The default deny policy is a security best practice. It blocks all ingress traffic by default, requiring explicit allow rules for any communication. This prevents accidental exposure of services. The allow policy demonstrates how to create specific rules for application communication. In this example, only pods labeled app equals web can communicate with pods labeled app equals API on port 8080. Network policies are enforced by the CNI plugin and work at the IP and port level. They complement Kubernetes RBAC and provide network-level security control, monitoring and troubleshooting. Effective monitoring and troubleshooting capabilities are essential for production shared VPC environments. The distributed nature of the architecture requires comprehensive observability. VPC flow logs provide detailed information about network traffic patterns. The sampling rate, 0.1, balances cost with visibility. You should adjust it based on your needs and budget. Firewall logging helps track security events and troubleshoot connectivity issues. Enable logging on security-critical rules to maintain audit trails. Common troubleshooting scenarios include connectivity issues between projects, incorrect IAM permissions, and IP range conflicts. Having proper logging in place makes these issues much easier to diagnose. Load balancer configuration. Load balancers are crucial for exposing your GKE applications to external users. In a shared VPC setup, you can configure load balancers in the host project to serve applications from multiple service projects, providing a unified entry point. Google Cloud offers several types of load balancers. Global HTTP/HTTPS load balancer for web applications, network load balancer for TCP/UDP traffic, and internal load balancer for internal services. Each has different use cases and capabilities. The global HTTP/HTTPS load balancer is typically what you want for web applications. It provides SSL termination, URL-based routing, and global anycast IPs. It can route traffic to backends in different projects within the same shared VPC. When configuring load balancers in shared VPC, remember that the load balancer resources, forwarding rules, target pools, etc., are created in the host project, but they can serve backends from any attached service project. This approach provides consistent external IP addresses and SSL certificates across all your applications, regardless of which project they are deployed in. Advanced monitoring setup. Comprehensive monitoring in a shared VPC environment requires coordination between the host project for network-level metrics and service projects for application-level metrics. This creates a complete observability picture. Google Cloud Operations provides powerful monitoring capabilities. For network monitoring, you'll want to focus on VPC flow logs, firewall logs, and NAT gateway metrics in the host project. These give you visibility into traffic patterns and security events. Application monitoring happens at the GKE cluster level in each service project. This includes container metrics, application logs, and custom metrics from your applications. Workload metrics help you understand resource utilization and performance. The key is correlating network-level events with application-level events. For example, if you see increased latency in application metrics, you can check VPC flow logs to see if there are network bottlenecks. Setting up proper alerting policies is crucial. You want to be notified of network issues like NAT gateway failures as well as application issues like pod crashes or resource exhaustion. Backup and disaster recovery. Disaster recovery in a shared VPC environment requires planning for both network infrastructure and application data. The shared nature of the network actually simplifies some aspects of DR planning. For network infrastructure, the host project contains all the critical networking components. This means you need to back up VPC configurations, firewall rules, and routing tables. Google Cloud automatically backs up most of this configuration, but you should document your setup. Application data backup happens at the service project level. This includes GKE workload configurations, persistent volume data, and any databases. Valera is a popular tool for Kubernetes backup and restore operations. Multi-region deployment is key for true disaster recovery. You can extend your shared VPC across multiple regions, allowing you to deploy clusters in different regions that share the same network infrastructure. Testing your disaster recovery procedures is crucial. Regularly practice restoring applications and network configurations to ensure your procedures work when you need them. Cost optimization strategies. One of the main benefits of shared VPC is cost optimization, but there are additional strategies you can implement to further reduce costs while maintaining performance and security. Resource right-sizing is crucial. Development and staging environments don't need the same resources as production. Use smaller machine types, preemptible instances, and auto-scaling to zero when possible. Network costs can be significant in large deployments. By using shared VPC, you eliminate egress charges for inter-project communication. Also, consolidating external connectivity through shared NAT gateways and load balancers reduces infrastructure costs. Implement automatic shutdown policies for non-production environments. Development clusters can be shut down during nights and weekends, staging environments during non-testing periods. Use Google Cloud's cost management tools to track spending across projects. Set up billing alerts and regularly review cost breakdowns to identify optimization opportunities. Security hardening best practices. Security hardening in shared VPC goes beyond basic configurations. You need to implement defense in-depth strategies that protect both network and application layers. Binary authorization ensures that only trusted container images are deployed to your clusters. This prevents malicious or unauthorized code from running in your environment. Pod security standards. Replacing pod security policies. Define security requirements for pods. Use restricted profiles in production to enforce security best practices like running as non-root and dropping capabilities. Network segmentation should be implemented at multiple levels. VPC-level firewall rules for coarse-grained control, and Kubernetes network policies for fine-grained pod-to-pod communication control. Regular security scanning of both infrastructure and applications is essential. Google Cloud Security Command Center provides centralized security insights across all your projects. Implement the principle of least privilege everywhere. IAM roles, service account permissions, network access, and application permissions should all be minimal but sufficient. Common troubleshooting scenarios. Troubleshooting in shared VPC environments can be complex because issues might originate from network-level problems in the host project or application-level problems in service projects. Connectivity issues are the most common problems. These often stem from incorrect firewall rules, missing IAM permissions, or IP range conflicts. Always start by checking the basics. Can pods reach the internet? Can they reach other pods? Can external traffic reach your services? Permission-denied errors during cluster creation usually indicate IAM configuration problems. The GKE service account needs specific permissions on both the host project and the target subnet. Double-check that all required roles are granted. Performance issues can be harder to diagnose. Use VPC flow logs to understand traffic patterns, and GKE monitoring to identify resource bottlenecks. Network latency between regions can impact performance significantly. Having a systematic troubleshooting approach is crucial. Start with network connectivity. Verify IAM permissions. Check resource quotas, and then dive into application-specific issues. Scaling and performance optimization. Scaling in a shared VPC environment involves both horizontal scaling, more clusters or projects, and vertical scaling, larger clusters or instances. The shared network infrastructure supports both approaches efficiently. Horizontal pod autoscaler, HPA, and vertical pod autoscaler, VPA, help optimize resource usage at the application level. Cluster Autoscaler handles node-level scaling automatically based on resource demands. Network performance is critical for microservices architectures. Use Google Cloud's Premium Network tier for better performance and lower latency. Consider node proximity and affinity rules to minimize cross-zone traffic. For very large deployments, consider using multiple clusters per environment. This provides better isolation and can improve performance by reducing the size of individual clusters. Monitor resource utilization closely and set up proper alerting. Use custom metrics to understand your application's specific performance characteristics and scaling triggers. Compliance and governance. Compliance in shared VPC environments requires coordination between network-level controls, managed by the host project, and application-level controls, managed by the service projects. This separation actually helps with compliance by providing clear boundaries. Audit logging is crucial for compliance. Enable audit logs for all API calls in both host and service projects. This provides a complete trail of who did what and when. Data residency requirements can be met by deploying clusters in specific regions. The shared VPC can span multiple regions while ensuring data stays within required geographical boundaries. Access controls should be implemented using IAM policies, and Kubernetes RBAC regular access reviews ensure that permissions remain appropriate over time. Documentation is essential for compliance. Maintain up-to-date network diagrams, security policies, and operational procedures. Many compliance frameworks require evidence of documented procedures. Migration and modernization. Migrating existing workloads to a shared VPC requires careful planning to minimize disruption. The approach depends on your current infrastructure and applications. If you are currently using separate VPCs per project, migration involves creating the shared VPC infrastructure and gradually moving workloads. Start with development environments to validate the setup before migrating production. Application modernization often happens alongside infrastructure migration. This is a good opportunity to implement cloud-native patterns like microservices, containerization, and automated deployment pipelines. Database migration requires special consideration. You might need to migrate from virtual machine-based databases to managed services like Cloud SQL, or implement database connectivity through private IP addresses. Plan for a phased migration approach. Move non-critical workloads first, validate functionality, and then proceed with production systems. Always have rollback plans ready. Future considerations and wrap up. As we conclude this comprehensive guide to GKE shared VPC setup, let us look at future considerations and summarize the key takeaways from our journey. Google Cloud continues to evolve its networking capabilities. Features like Private Service Connect, Traffic Director, and advanced security controls will enhance shared VPC capabilities. Stay current with Google Cloud releases to take advantage of new features. Consider adopting GitOps practices for managing your infrastructure. Tools like Config Connector allow you to manage Google Cloud resources using Kubernetes manifests, providing version control and automated deployments. Multi-cloud and hybrid scenarios are becoming more common. Shared VPC integrates well with Google Cloud's Anthos platform for managing workloads across multiple environments. Remember the key principles we have covered. Proper IP planning prevents future issues. Centralized network management simplifies operations. Security should be implemented at multiple layers, and cost optimization is an ongoing process. Your shared VPC implementation is the foundation for scalable, secure, and cost-effective Kubernetes infrastructure. With proper setup and ongoing management, it will serve your organization's needs as you grow and evolve.